Welcome to Review for Final Exam and Course Conclusions. This is the very last lecture in Organic Chemistry 1. So let's look at this slide real quick. This is a typical winter scene that many of us are experiencing as we speak. Interesting interview of Albert Einstein on his 50th birthday in 1930 by George Sylvester Weyrach. I want to read this to you real fast. Do you believe in God? I'm not an atheist. I don't think I can call myself a pantheist. The problem involved is too vast for our limited minds. We are in the position of a little child entering a huge library filled with books in many languages. The child knows someone must have written those books. It does not know how. It does not understand the languages in which they are written. The child dimly suspects a mysterious order in the arrangement of the books, but doesn't know what it is. That is, it seems to me, is the attitude of even the most intelligent human being toward God. We see the universe marvelously arranged and obeying certain laws, but only dimly understand these laws. What would Einstein think of the unraveling of the human genome today? I think he would be pretty impressed. Okay, let's look at some basic concepts through this semester. But first, before we look at the very basic concepts, here's just a few comments about the final exam preparation. I've listed here all the things you really should review. Follow the some important things to remember in each of the chapters. Go through those and follow those concepts. Certainly look at the old quizzes, homework problems on mastering chemistry, problems in the chapters at the end of the chapters, and also the summaries at the end of the chapters are very good for review. And of course, your file cards with the reactions, class notes, and mainly problems, questions that you've answered. We're just going to run through the chapters, and I'm going to mention a few of the most important concepts we've studied during the semester, things that have come up over and over again. This is the only way we can discuss all of the semester in just a few minutes. It's impossible to cover everything, obviously, but these are just some things that I think are very important for our understanding of organic chemistry. So, Chapter 1, Electronic Structure. The more S character in the orbital of a given atom, the shorter and stronger the bond. The larger the bond angle and the more electronegative the atom. So I've just made some basic statements on these slides. Also, formal charge. Be able to calculate that and determine that for an atom. And of course, here's the definition of it: the number of valence electrons minus the number of lone pair electrons plus 1/2 the number of bonding electrons. And this diagram, or these compounds that are drawn here in this diagram, are illustrating how we can write the various structures, showing the electrons to calculate the formal charge. For example, this one right here, oxygen, on this molecule. The number of valence electrons is 6. The number of lone pair of electrons is 4. 2 plus 2 is 4. Plus 1/2 the number of bonding electrons. There's 2 here and 2 here, so 1/2 of 4 is 2. 4 plus 2 is 6. 6 minus 6 is 0. And 0 is the formal charge on oxygen. Notice there's no plus or minus because it's neutral, it's 0. You can look at the others and calculate them for yourself. One correction on this slide, this example here, notice this is just an oxygen atom with a negative charge. Over here, the hydrogen needs to be deleted. Otherwise, it's correct. Okay. Also, as we moved into organic chemistry in the beginning of the semester, we talked about acids and bases. The stronger the acid, the more readily it gives up a proton. The stronger the acid, the lower its pKa. Acid strength depends on the stability of the base formed when the acid gives up its proton. The more stable the base, the stronger its conjugate acid. Or the weaker the base, the stronger its conjugate acid. Also, chapter 2, going, and again, acids and bases, going across a row in the periodic table, the more electronegative the atom to which the hydrogen is attached, the stronger the acid. Certainly, electronegativity, fluorine, oxygen, nitrogen, carbon is a sequence. Of course, fluorine is over to the far right in the periodic table, and then to its left, oxygen, to its left, nitrogen, to its left, carbon. And electronegativities are in that, and as you can see the pattern on the slide. Also, another pattern of electronegativity we've seen is sp orbital, molecular hybridized orbital, is more electronegative than an sp2 than an sp3. Notice S characters, 50%, 33%, 25%. Also, acids and bases, going down a column in the periodic table, the larger the atom to which the hydrogen is attached, the stronger the acid. A compound exists primarily in its acid form with its proton in a solution that is more acidic than its pKa, and in its basic form, that is without a proton, in a solution that is more basic than its pKa. This is described by the Henderson-Hasselbalch equation. In fact, that's what the Henderson-Hasselbalch equation states itself. When you look at the equation, this is a fundamentally important equation to understand how to use. This is just a generic overall equation of an acid losing its proton, becoming a conjugate base. You can see pKa equals pH plus the log of the concentration of the protonated acid divided by the concentration of the acid once it's lost its proton. And this could be derived, and certainly in many advanced courses of chemistry it is. pKa is a characteristic factor of a chemical compound that doesn't change. pH is just the characteristic of a solution that certainly can change. So this is a fundamentally important equation to learn how to use. Certainly nomenclature. A compound can have more than one name, but a name must specify only one compound. The systematic name of a compound is obtained by using a set of nomenclature rules, which we've used all along, and they're very much similar from one group to the other. The number of alkyl groups attached to the carbon to which the OH group is attached determines whether an alcohol is primary, secondary, or tertiary. The number of alkyl groups attached to the nitrogen determines whether an amine is primary, secondary, or tertiary. The cis isomer of a disubstituted cyclic compound has its substituents on the same side of the ring. And of course, we've dealt with trans. The isomer of a disubstituted cyclic compound has its substituents on opposite sides of the ring. Just basic terminology and understanding of what cis and trans mean. A chiral molecule has at least one asymmetric center and does not have a plane of symmetry. Compound with one or more asymmetric centers will be optically active except if it is a meso compound. You might hone in on meso compounds. For example, a meso compound has two or more asymmetric centers in a plane of symmetry. If a compound with two asymmetric centers has the same four groups bonded to each of the asymmetric centers, one of its stereoisomers will be a meso compound. Here is an example of a meso compound. Cis-1,2-dibromocyclohexane is a meso compound. And notice it has two asymmetric carbons, or centers. So 2 raised to the second power equals 4 enantiomers would be expected. But we have a meso compound that actually represents 2 of the 4. Therefore, there are just 3 that we can draw. Here are trans 1,2-dibromocyclohexane, a pair of enantiomers. Here's several other terms, stereochemistry, that are often used throughout organic chemistry, and that's regioselective reaction forms more of one constitutional isomer than of another. A stereoselective reaction forms more of one stereoisomer than another. In a stereospecific reaction, each stereoisomeric reactant forms a different stereoisometric product, or a different set of stereoisometric products. We use regioselectivity, stereoselectivity, and stereospecificity often to describe compounds. Electron-rich atoms or molecules are attracted to electron-deficient atoms or molecules, and that is, nucleophiles are attracted to electrophiles. Normally, generally negatively charged nucleophiles and positively charged electrophiles. The general molecular formula for a hydrocarbon is C sub n, H, or the number of hydrogens, 2n plus 2, minus 2 hydrogens for every pi bond or ring present in the molecule. As long as each of the sp2 carbons of an alkene is bonded to only one substituent, cis and trans terms can be used. If the hydrogens are on the same side of the double bond, it is cis. If they're on opposite sides, it's trans. If the sp2 carbons are bonding more than one substituent, the cis-trans system of nomenclature cannot be used. The EZ system of nomenclature was devised for these kinds of compounds. The Z isomer has the high priority groups on the same side, similar to cis. Also in chapter 6, reactions of alkenes, here is the carbocation stability sequence that we have used many times in our course. Tertiary, of course, is the most stable. Then we have primary benzyl structures. Then we have primary allele, and that are about equally strong as tertiary. Secondary and primary. And methyl and vinyl carbocations are way over here to the right. Probably we should remove this tertiary right here. That doesn't belong there. It's way over here on the left. So put a line right through that. In an electrophilic addition reaction, the electrophile adds to the sp2 carbon bonded to the greater number of hydrogens, Markovnikov's rule. Certainly an important concept to remember. Reduction increases the number of carbon-hydrogen bonds or decreases the number of carbon-oxygen, carbon-nitrogen, or carbon-halogen bonds. Oxidation decreases the number of carbon-hydrogen bonds or increases the number of carbon-oxygen, carbon-nitrogen, or carbon-halogen bonds. Alkene stability, the greater the number of alkyl groups bonded to the sp2 carbons, the more stable the alkene. We've seen this over and over. Alkyl substituents stabilize alkenes, alkynes, carbocations, and radicals. So this kind of summarizes when we pay attention to to alkyl groups. Okay, one more slide, and I think we will conclude part 1 of this final lecture, and that is reactions of alkynes. This is chapter 7. Alkenes and alkynes have the same regioselectivity in electrophilic addition reactions. The electrophile adds to whichever sp2 carbon or sp carbon is bonded to the greater number of hydrogens. Markovnikov's rule. Because an sp hybridized carbon is more electronegative than other carbon atoms, terminal alkynes have acidic properties that are useful for synthetic schemes in which the number of carbons in a reactant needs to be increased so we can build molecules. We'll stop right here.